I want to take a moment to address the question, why two methods? Why two ways to do this? So, this is a figure, this is our region, is bounded by the line y equals negative 2x plus 3. This is the line here. It's the parabola y equals x squared, and it's bounded by the y-axis. So it's this piece here, and we're going to revolve this about the y-axis, and if we do that, we generate this solid in three-dimensional space. It's sort of like a little spinning top kind of a thing. But that's our figure we're going to generate. Now, suppose we want to find this volume, the volume of this solid, using the disk method, Okay, if we're revolving about the y-axis and we're using the disk method, the first question is, what is the axis of partition? Well, for the disk method, the axis of partition is the same. So we have to partition bottom of figure to top of figure. We would partition all the way from 0 to 3, right? And so here, the volume, well, the multiplier is just pi. Integral, and we do know is going to be dy, which means we stink and might as well go ahead and do this now. Go ahead and solve these functions to make them functions of y instead of functions of x. Well, if you do that for here, what do you get? You get y minus 3 over negative 2. Does that look right? So here we get y minus 3 over negative 2 is equal to x. And here we get the square root of y is equal to x. So I'm solving both of these functions for the other variable because we know we need to have everything in terms of y. Now, there's an issue, however. So don't write this in yet, but it looks like you might just go integral from 0 to 3. But the problem is this. As you pass from 0 to 3, as soon as you hit the function value of 1, do we see this point? This is a cusp. And now at a cusp, the derivative and hence the antiderivative is not defined. And so we cannot write this as a single integral because you're passing over this cusp. You would need to break this. If you're going to use this disk method, you would need to break this into two pieces. One for the disks down here using the parabola to determine the radius, and the other for the disks up here using the line to determine the radius. And so if we're going to use the disk method, you would need to break this into two integrals. The first, let's use the first for the parabola portion. Here, the integral goes from 0 to 1 because the parabola only goes from 0 to 1. And then we need the radius. Well, the radius is the function value, right? The radius is the function value. And the function value of the parabola is square root y in terms of y. So that's square root y quantity squared. And I'll go ahead and move this over a little bit. So we have pi times the radius squared times the thickness. And that gives us the volume of just this bottom curved portion. Now we want the top value of this top. It's actually just a cone. But we want to find the volume here with an integral. So now we do the same thing. Pi integral. It's still dy. But now the limits of integration for the straight line portion go from 1 to 3. And I need the radius squared. But here the radius is the function value of the line. Here the function value is the line. And so that's the radius. We have y minus 3 over negative 2 quantity squared. So in this case, set up integrals, integral or integrals. Sorry, this is not equals, this is plus. So this is pi times this plus pi times this. This gives you the volume of the bottom of the picture. This gives you the volume of the top of the picture. Sum those to find the total volume using the disk method. All right. Now, let's back up the train and do the whole problem again using the shell method. See if I can get my pictures drawn here. I don't need that piece. But if we want to see the picture drawn, it would look something like this. All right. But now we're going to use the shell method. So let's get rid of this. All right. The shell method, we're revolving about the y-axis. So the partition is the opposite axis. So the shell method, we need the volume. First off, the multiplier is 2 pi with the shell method. And we're going to use dx. The axis of partition is the opposite axis. 0, 1. This is 1. This is 3. So we partition the other axis. This is the integral from 0 to 1 using the shell method. Also, since we have dx, then we know we're using these original expressions. One reason that might make the shell method more advantageous is, let us suppose that maybe one of these functions is much more complicated. It has a inverse tangent, or it has some x squared plus natural log. It has some weird way to solve it. And if you want to solve for the other variable, that might be either very, very difficult or very, very time consuming, or maybe just not possible. So if that's the scenario, don't use that method. That's one of the reasons we want to have two methods. But be that as it may. So we're using the x variable. So this is the partition from 0 to 1. So far, so good. The rectangle now goes vertically because the partition is here. And using the shell method, we need rho for the radius, and we need h for the height. Well, if you're revolving about the y-axis, this is always the case, world without end, amen. If you're revolving about the y-axis, the shell method radius is the x-coordinate. The height is top function minus bottom function. So all we need is top function, which in this case is the line, negative 2x plus 3, minus the bottom function, and the bottom function is the parabola, and you're done. One integral does it at one shot because as far as the shell method is concerned, you're not passing over the cusp. The cusp is the right endpoint, and so you never pass over this cusp. If that's advantageous, then you would use the shell method if you want to only use one integral. So sometimes both of them are viable. Sometimes one is just about as easy as the other. There are circumstances where one or the other of the methods may have advantages that the other doesn't possess. And so it is convenient to be able to work these integrals or find these volumes using both of these methods.